Hello, everybody. While you're all taking your seats, I would like to welcome you to the Neutrino Frontier plenary session. First of all, I'd like to remind you of the code of conduct, which is always useful to keep in mind. And the proceedings are going to be like follows. We're going to have 3 talks, one by Marc Messier on neutrino oscillation, followed by a talk by Andre Dugueva on neutrino theory, then followed by a talk by Kate Scholberg on sort of astrophysical neutrinos in the widest sense. And then we're going to have left time for questions. The talks are each about 20 minutes, so there should be plenty of time for questions. We'll take questions for all talks at the end because the talks are quite interconnected, and the hope is that many of the questions you have are answered by one of the other talks. All right, without further ado, Marc, you have the stage.
Very good. All right, well, while they're bringing the slides up, it's great to see so many of you. It's been really a wonderful week, and I want to thank the organizers for hosting us at such a beautiful location and providing for such wonderful weather. Okay, are we ready to go? Very good. Okay, so I'm going to tell you a little bit about neutrino oscillations, 3 flavor oscillations and beyond. And the story of neutrinos and neutrino oscillations is really a story of neutrino mass. And earlier this month, we celebrated a 10-year anniversary related to mass, which was the discovery of the Higgs boson. The Higgs boson is necessary to give the standard model charged fermions their masses. The standard model is complete with the Higgs boson, but it points to ways in which it is not complete. And I think we heard much better descriptions of that before the break than you'll get from me. But the fact that the particle that gives mass has a mass requires new physics to stabilize its self-energy. And that's associated with the scale that could be as low as the TeV scale. And the fact that the 3 standard model forces unite at some very large scale, the Guts scale, points to a very large and high energy scale where we expect new physics. What the standard model doesn't explain is observations that go back 20 years, which is the observation by the Super Kamiokande experiment and the SNO experiment that in fact neutrinos oscillate and therefore must have a mass. With the observation of neutrino oscillations, we now know that we need a neutrino mass of at least 50 milli electron volts. And so we can go back to our picture here, and we now know where to put neutrinos on this scale. So we know from direct experiments, direct observations, that the neutrinos must be less than about an eV in their masses, but we now have experimental evidence that there must be at least 1 and 2 neutrinos that have masses on the scale of 50 milli eV. What remains unexplained is this large gap between the standard model particles and the neutrinos, and then this large gap where we expect to be new physics. The standard model can't accommodate neutrino masses on its own, but if you introduce a new field, a right-handed, a new right-handed field, one can then form neutrino masses. Naturally, one has to introduce a new mass scale for that field, so-called Majorana mass. The eigenvalues of this matrix then work out to be something like this, something like the Dirac masses squared divided by that Majorana mass. And if we start playing with the numbers that we know, the scale at which experiments tell us the neutrino masses must be, the scale at which the standard model Dirac masses are, the new field that we have to introduce naturally comes out to be the scale that we already expected new physics to appear at, something between the TeV and Guts scale. And so neutrino masses really require new physics, and new physics that approaches the Guts scale. And so neutrino oscillations are a way of probing this new energy regime. So neutrino masses are very small. That makes them difficult to detect directly. And so we're forced to go to an interference experiment, which is what all experimentalists do when they want to measure something small. You do an interference experiment. In this case, the interference experiment is the neutrino interfering with itself. Like all things in quantum mechanics, you can think of it almost like a 2-slit experiment, except in this case, there are 3 neutrinos, so it's like a 3-slit experiment. The idea is that you start with a coherent state, a neutrino of definite flavor, alpha. It's going to propagate from the source to the detector through space. It has essentially 3 choices for how to do that. It can propagate as the lightest state, the heaviest state, or the one in the middle. Each of those states accumulates phase differently. And so when you come to detect it, there's an interference between those 3 possibilities. And this is what we see as neutrino oscillations. We often parameterize this as the mixing of this state alpha into the three states nu1, nu2, nu3 as a product of several matrices. It's convenient to do that because the frequencies at which these oscillations happen are different by about a factor of 30 or so. And so in many cases, we can think of these as sort of two neutrino processes instead of having to work with the full three flavor all at the same time. And so we have what's called the 2-3 sector here, the 1-2 sector here. This has largely been explored through atmospheric neutrinos and now with experiments at accelerators at long baseline. These 1-2 couplings have been explored with solar neutrinos and have been explored with reactor experiments and will be explored more with reactor experiments in the future. And this 1-3 is often called the reactor matrix. It's important for long baseline experiments, but the first really conclusive evidence that this matrix had a large value of this angle theta 1-3 came from reactors, and it's often associated with that. So the mixings determine the amplitude of these oscillations, and so we parameterize that as trigonometric functions of the mixing angles. And then there's a frequency that depends on this mass splitting. And crucial for the experimentalists, your baseline L and divided by your energy E tells you what scale at which you're probing the mass splittings. We know quite a bit with data gathered over the past 20 years about what that matrix looks like. It's a little bit easier to understand in this cartoon form. We know that there are two neutrinos that are close in mass, and they hold most of the electron neutrino flavor. We don't know whether those two states are the lightest two states or the heaviest two states. That's something referred to as the mass ordering question or the mass hierarchy question, depending on who you were talking to. We know that angle is fairly large. We know it's not maximal, but it's somewhere between 31 and 36 degrees. This angle controls how much electron neutrino flavor there are in this lowest state. We know from looking at atmospheric neutrinos that there's a very large splitting to the third mass state. That mass state is almost equally split between nu mu and nu tau. If this angle were 45 degrees, it would be exactly a 50-50 match between the green and the blue. And the best data we have is that that angle is in fact consistent with that maximal value spread around that 45 degrees like this. You'll notice that if that angle is 45 degrees, in fact, you can interchange the green and the blue, which is interchanging the muon and tau flavor everywhere, and not change the neutrino mixing pattern, which is perhaps an interesting symmetry. The last angle to enter this picture is actually now one of the best and most precisely known, which is this angle theta 1-3. That one, roughly speaking, controls how much electron neutrino flavor is in this third state. That's the smallest of the three angles, but it's still quite a large angle, and it could be between 8.2 and 9 degrees. Having all of these mixing angles be large gives us a really great opportunity because all of the mixing angles are large, it means that the neutrino mixing and the quark mixing look very different from each other. This has really important implications for whether or not we can measure CP violation and what the possibilities are for measuring CP violation in neutrinos. In quark mixing, things are nearly diagonal, and there are these very tiny elements off to the side. And if you compute how large the CP violation can be, it actually involves every single one of these matrix elements. For the neutrinos, because all of the angles are relatively large, even that smallest one, which is just about 8 degrees, all of the mixing elements are large. And so if you compute the ratio of how large could CP violation in neutrinos be in ratio to how large the CP violation is in the quarks, you find that it could be almost a factor of 1,000 larger, depending crucially on the sign of this complex phase that appears in the mixing matrix. And so CP violation in neutrinos could be 1,000 times larger than it is in quarks and presents a real opportunity for discovery. Okay, so going beyond that simple picture, what would it take? And I'm going to take just as an example, an experiment that is rapidly coming to the end of its construction and will soon be taking data, and that's the genome experiment. This is the next generation reactor experiment. It will construct a 20 kiloton liquid scintillator detector. That's a factor of 2 more liquid scintillator than we've ever built for the largest detector, the NOVA experiment. That detector will sit about 50 kilometers away from 2 very high-powered reactors. You can see that construction of the acrylic vessel is nearing completion there. And so operation, we expect to begin in 2023. I want to call your attention to the y-axis here. So this is the spectrum of neutrinos that Juno expects to see, just to give you some sense of what the next generation is going to take. This is not 100 events, but 100,000 events at the top of this axis. And so this experiment will see tens of thousands of events in every MEV bin to do its physics. And what that allows is to really move from sort of a discovery phase into a precision phase in neutrino physics. To highlight some of that precision, these are the improvements that one will see in these delta m squareds 3.1, 2.1, and then this solar mixing angle sine squared theta 1.2. Current knowledge is represented by these chi-squared surfaces here. And then after 6 years of Juno data, one would see these red curves that are shown in the 3 panels. Almost an order of magnitude improvement in the precision of each of those parameters. So we have precision, but we also have some big questions that still, some qualitative big questions that we still need answers to. So going back to my cartoon, we want to know if this mu tau symmetry is real. Remember that angle is 45 degrees, but with about a 5-degree uncertainty. If it is a true symmetry, that would be very interesting and maybe points to what the underlying correct model of neutrino masses is. We don't know what the ordering of the neutrinos is. We think of the one that has the electron neutrino is associated with the light flavors as being normal. We think of it when the electrons are heavy as being, inverted or the upside down ordering. So we don't know which of these two is true. Remember that there's really no reason to believe that the neutrino masses should be ordered the same way as the charged fermions because they seem to be getting their masses from very different mechanisms. So this is largely an experimental question that needs to be resolved. We'd like to know if CP is violated. That hinges crucially on the size of that, the participation of the electron neutrinos in that third state. And then really, we would like to know, is this the whole picture or is there more to this? Remember, we're integrating over possibly very large energy ranges, energy scales where new physics could appear. And so if new physics talks to neutrino oscillations, we really want to see if this is all there is or not. So I'll bring you up to date on where we are with the current generation of experiments. Roughly speaking, this is the TDK experiment and the NOVA experiment. TDK uses a 500 kilowatt source at the J-Park accelerators, sends a neutrino beam across Japan to the Super Kamiokande detector. Similar experiment, NOVA, uses the accelerators at Fermilab, which have recently achieved 900 kilowatts of power, sends their neutrinos 810 kilometers to our detector in northern Minnesota, seen here. Difficult to get the scale, but there's a person standing there for scale. Both of these run at roughly the first oscillation maximum and have reported data with both neutrinos and antineutrinos. So here's some data looking at that question of the mu tau symmetry, which one does by looking primarily to see if the muon neutrinos you produce have survived to your far detector. This case of perfect symmetry is the line down the middle, and you can see the data from TDK and NOVA are maybe slightly pulling into this upper octant, but still the error bars are quite large and unable to resolve whether or not they have pulled far enough away from that symmetry point. So it's an interesting symmetry, something we want to follow up on. Looking in the appearance channels, this is the two channels that are mostly related to CP symmetry and hierarchy. The TDK experiment has recorded approximately 100 events in their neutrino mode and 15 events in their antineutrino mode. The normal hierarchy choices are the ones in the lower right. The inverted are the upper left. As you go around these ellipses, you're varying the CP phase. And so TDK sees a relatively large number of neutrinos and a relative deficit of antineutrinos, which suggests strong CP violation. But if we look at the data from NOVA, you'll notice that we see kind of the opposite. We see not quite as many neutrinos as the TDK data might imply. And actually, with a data set which is almost twice as large in the antineutrino mode, we see a relatively large excess of antineutrinos over what TDK might predict. So really, I think if you put these two together, and the experiments are working on a joint fit, it's really unclear what the landscape is telling us. CP violation could be large, but there's still quite a range of possibilities that are open. And in fact, the hierarchy question is also still quite wide open. While each individual experiment favors the normal hierarchy, because of this arrangement of data, there's actually a possibility that the two combined favor the inverted hierarchy. Okay, so how are we going to go even further beyond T decay and nova? And for those of you sitting in the front, I'm going to warn you about waving hands. Okay, most of the questions that we're really interested in are questions of CP violation and the mass hierarchy. And those basically come down to, is this ratio of the oscillation probability of anti-muon neutrinos to anti-electron neutrinos divided by the probability for muon neutrinos to go to electron neutrinos 1. Experimentally, how do we do that? We count events. And when we count events, we produce a flux of neutrinos. They oscillate as they travel to our detector, and that's where the physics that we're interested in. They have a certain cross-section to interact in our detector. Our detector has a certain efficiency for seeing them. And so we do that twice, once for neutrinos and once for antineutrinos. If I solve for the thing that I'm interested in, that is a ratio of two fluxes, a ratio of two cross-sections, a ratio of two detection efficiencies, and then the event counts. If I want to know if this is 1 to within, better than 1%, which is what the next questions are going to demand, I need to control all of these other ratios. I need lots of events to get the error bar on that ratio down. And then I need to understand my fluxes, my cross-sections, and my detection efficiency. So how does one do that, given that there's a priori relatively large differences in these ratios? Detection efficiency, neutrinos and antineutrinos interact differently. Your detector is going to respond differently. Neutrino fluxes, we produce our neutrino beams with protons. We also produce our anti-neutrino beams with protons. We can't produce it with anti-protons. And so there's a flux difference that could be as large as 15 to 30%. The cross-section ratio is almost a factor of 2 to 3, depending on the energy you're working at between neutrinos and antineutrinos. And so in order to control all of these, the experiments are designed to have near detectors. But then that's only the first order. To go to the next order, to get to that 1%, really requires a great deal of work. And so the things that are needed to get these differences down to the 1% we need, obviously we need large FAR detectors and intense beams to control the error bars on just the event count ratio. We need very capable near detectors to characterize how well how efficient our detectors are and how they respond to neutrinos and antineutrinos. We need highly capable FAR detectors and near detectors. We need test beams to characterize those. To understand the flux, we can measure the flux in situ with our near detectors. We can also do dedicated production experiments to understand the processes that we use to make our beams. To understand the cross-section ratio, again, the near detectors have an important role to play in understanding the cross-sections, but also we need a dedicated measurement and theory program to really understand those cross-sections. And again, how well we measure cross-sections is coupled to how well we understand our detectors, and so test beams are a necessary component. Okay, so 20 years ago, we discovered neutrino oscillations. It launched a rich program. There's no way I can cover all of that program. This is an incomplete slide listing all of the experiments within the neutrino frontier. And as a function of date and sort of where they are in either data taking stage or approval stage, you see it's a very rich and active program, in part because we need to understand all of those components: the flux, the cross sections, the detectors. I'm going to highlight just a couple in the remaining time in my talk. So the T to hyper K experiment is the next generation to super K. So Kamiokande saw neutrinos from the sun. Super Kamiokande discovered neutrino oscillations and atmospheric neutrinos. The next generation is another order of magnitude scaling up, which is the hyper Kamiokande experiment, and which will become the new target for the J-Park accelerator beam in the next generation. So data taking for that is expected to begin in 2027. The excavation has just reached the top of the large cavern, and the excavation of that cavern is to begin soon. Within 10 years, they expect a 5 sigma discovery of CP violation for a large number of possibilities of that CP violating phase. And that's the summary of this plot in the upper right-hand corner here, where the significance is going up the y-axis, and the value of that delta CP phase is going across on the horizontal. The search depends strongly on resolving the mass ordering and controlling systematic uncertainties. And you can get some sense of that by looking at the evolution here. Again, it's significance for the CP observation on the y-axis, and then years. And you can see what the statistics and then improved systematics, and then if you only had the current systematics. Current understanding of systematics is this lower curve, and improved, and then statistics only is here. So again, those factors that I mentioned are really crucially important to the future discovery. In the US program, our program is centered around the DUNE experiment. This will use the beam at Fermilab, directed over a very long baseline, 1,300 kilometers, to a series of new detectors at the SURF facility. These are enormous detectors. Each one of these modules is as large as NOVA, but whereas NOVA instruments with centimeter scales, these are going to be able to resolve neutrinos at the millimeter scale. So these detectors exist. This is a beautiful picture of the largest liquid argon detector in existence, which is operating in the test beam at CERN, just to give you an idea that this is not a future thing, this is a now thing. And this gives you some idea what the capabilities of this technology is. So this is a detector module. It's roughly the size of an office building, but you can resolve these neutrino events with just exquisite detail. These top two are simulations, but this is a real event that was taken at the CERN test beam. That's a real 6 GeV electron, as seen by the Dune TPC. So what might we be looking forward to roughly 10 years after Dune takes its first data? This is the nu-mu spectrum. This is the anti-nu-mu spectrum. And then these are the electron neutrino appearance experiments. So this is roughly the state of Dune at the end of what is now being called phase 1 that begins in 2029. The thing I find truly remarkable about this is, remember that mu-tau symmetry question. If there is a mu-tau symmetry, this bin would go all the way to 0. And so now that question about whether that mu-tau symmetry is real isn't hinging on handfuls of events, it's hinging on almost 160 events. And so the fact that this is 160 events above 0 is telling you that that symmetry, in fact, is broken. In phase 1, the primary physics mission is to resolve the mass ordering at 5 sigma. In phase 2, one begins to really push on the CP violation and then try to go beyond questions that one asks with the PMNS matrix. Again, realizing the full experiment is crucial to all of this. Controlling every one of those factors, the statistical errors on the event counts, and then all of the systematics is really important. So if one continues with the Dune phase 1, which is 2 detector modules, you can see the significance for measuring CP violation kind of peters out at about 3 sigma. But if one builds the full experiment and realizes the full experiment with 4 modules, you can see that then exceeds 5 sigma. Likewise, with the proton source, if you continue with the 1.2 megawatts of Dune phase 1, you peter out at about 3 sigma, and one would really like to go to the 2.4 to maximize the potential for CP violation measurements. The near detector plays a crucial role to this. In fact, it's almost as important as the beam upgrade and the detector, the far detector upgrades. Again, one sees the impact of limited systematics kicking in that phase 2, but the improved and upgraded near detector brings you to that top red curve. Why do we want this precision? What's the payoff for getting this precision? Well, if we really are able to measure all of these parameters precisely within the PMNS framework, we can begin to sort out what the underlying models of neutrino masses are. We don't know what the underlying symmetries are of neutrino masses, but various approaches to neutrino mass make predictions. They make predictions about the ratios of the mass splittings to some of the mixing parameters. They predict whether the mass ordering is inverted or normal. And so if we have precision measurements, we can begin to test these predictions from the theories and sort out what the underlying theory is. An example of that is this plot here, where 6 different approaches to neutrino masses make 6 different predictions of the cosine of the CP violating phase delta. You can see they appear at 6 different places. The width of these depend on the neutrino oscillation parameter inputs. And so as we improve the precision, those get tighter. And then as we have a measurement of cosine delta, maybe we can begin to decide and discern among these models. At that point, PMNS matrix becomes a background. And that's really the point where we would get to. Once we understand the PMNS oscillations, we can now treat that like a background for studying physics beyond the standard model. And to give you some idea of what the potential of that would be with Dune, here's a plot looking for a sterile state that might populate this gap in the mass spectrum. And you can see that going into that second phase of the Dune experiment, one would be able to extend this search for sterile or dark sector particles by almost 2 orders of magnitude in some cases. That's where we would really like to get. So this brings me to that summary. Neutrino oscillations are an open window on new physics. And we have big questions to be answered about symmetries, about the mass sorting, about CP violation. The key to answering those questions is going to be precision. And the key to moving beyond answering those questions is also going to be precision. And so the future is a worldwide endeavor. It's going to require a diverse program of experiments on multiple scales. And in the US, that program is going to be anchored by the Dune experiment. Thank you very much.
Thanks. Thank you, Mark. As I said in the beginning, we'll take questions for all three talks at the end. And the next speaker is Andre.
What's your preference, Andre? Thank you. Okay. I think it's already on.
Down is forward, okay. Oh, and the laser pointer is at the bottom. Okay, let me continue on where Mark left off. So my job is to tell you about beyond the standard model physics in the neutrino frontier. I will be telling you along the ways that I have to make lots of choices because I only have 20 minutes and I'm running out of time. So let me get started. So I have four main messages I wanted to leave you with. One is to remind everybody what Jesse has already said and lots of people have already said, and Mark has already said, is that neutrinos are physics beyond the standard model. So I will tell you a little bit about that and why that's an interesting question and why that's a very hard question to address experimentally. I will then tell you about the fact that there could be more physics in the neutrino sector, including the physics that gives neutrinos a non-zero mass. And I'll try to give you some examples of that. I won't have too much time to also tell you about the fact that neutrino experiments are great beyond the standard model search engines. And we have to exploit that as much as we can. And that will require that we understand neutrino cross-sections very well and that we have very nice near detectors. And finally, I will remind you of the fact that it is possible that we've already run into more new physics in the neutrino sector, but we're not sure. So we need to find out. Again, I will have to pick and choose lots and lots of topics among a very broad spectrum. There are lots of white papers on beyond the standard model physics in the neutrino sector. This is not all of them. There were lots of talks on looking for beyond the standard model physics in the neutrino sector at Snowmass, and I invite you to look at the slides. I will say when I was thinking about this, I remember 3 other white papers that I should have cited, but I forgot. So very quickly, because Mark already told you about this, neutrino masses are very interesting because they're not zero. And they're extra interesting because they're very, 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 very small. And I think it's important to keep that in mind all the time. And I think as Mark tried to emphasize as well, neutrino masses are not just very small, but they're very different. So they don't seem to fit into this very, very broad view of where the charged fermion masses fit, because all the charged fermion masses live up here, and they only span about 5 orders of magnitude, and we've grown accustomed to that. But neutrino masses live all the way down here below, let's say, 0.1 electron volts, and insult to injury, there's this big gap where we don't think there are any new particles there. And then on top of that, the standard model of particle physics predicts, as Jesse told us earlier today, if you take everything at face value, that neutrino masses are 0. And I do want to say that's a great prediction. It works really well because the masses are super small, but not perfectly. So what do I mean by the fact that neutrino masses are physics beyond the standard model? What I mean by that is that if you want to accommodate neutrino masses, you have to add new fields to the standard model of particle physics. So there's some new particles out there. Maybe they're right-handed neutrinos and they're kind of boring, but that's a particle that we didn't have there to begin with. And if you think about it for a while, what makes the problem interesting is the fact that we can invent mechanisms to generate non-zero neutrino masses where the new particles that I'm adding in are very heavy, or they're very light, or they're bosons, or they're fermions, or they're very easy to find in the particle physics experiment, or they're virtually impossible to find in the particle physics experiment. And as, for example, Hitoshi told you about in the very first day, there's a small number of very concrete things that the standard model doesn't know how to explain, and neutrino masses is in this list. Very, very quickly, just to give you a flavor of where neutrino masses could come from, Of course, they have to come from electric symmetry breaking. That's not a choice. That's the thing that has to happen. What happens with neutrinos is that you have some obvious choices and we don't know what the right choice is. It is possible, for example, that neutrino masses come directly from the Higgs. That would be weird for different reasons that I want to talk about because I don't have a lot of time. Neutrino masses might be a consequence of the fact that electric symmetry breaking is more complicated, and maybe there are more Higgses, and maybe there's a special Higgs just for the neutrinos. And that's another possibility. And a third possibility is that maybe there's another source of mass out there, some new mass scale that has nothing to do with electric symmetry breaking, and neutrino masses are a mixture of the electric symmetry breaking scale and this new source of mass. If you think this sounds very complicated, everybody thinks this is the right answer for lots of reasons. And of course, we would like to learn experimentally what the right answer is. Just to make life harder, I don't know even the mass scale of where things are going on. And the mass scale can be anywhere from below electron volt scale all the way to a ZeV, which is a cool unit, so we should all keep that in mind. And there's this whole parameter space that we need to explore, and the way in which we explore it is just completely different. So if we have new physics at the MeV scale, the way that I look for that is completely different than if I have new physics at the ZeV scale, and God help us explain how to search for that. But the consequences of these different types of physics are also completely different. So if we want to solve this neutrino mass puzzle, we need a lot of help. And the place where information might come from is incredibly diverse. It can come from neutrino oscillation experiments. It can come from neutrinoless double beta decay. It can come from experiments involving charged leptons. Remember, charged leptons and neutrinos are friends. It can come from the LHC. It can come from cosmology. And it can come from astrophysics. Now, it's important to say that I always said it can come. It doesn't have to come from any of these places. But that's life. That's how physics works. I want to concentrate on neutrino oscillation experiments because I don't have a lot of time. I also want to remind you of this amazing fact that neutrino masses are really small. And I've said that already many times. And we've only seen the consequence of a non-zero neutrino mass in neutrino oscillation experiments. We've been trying since the 1930s to detect a non-zero neutrino mass. It was Fermi's idea. Fermi was very smart, and he didn't do it because he didn't have the technology to do it. And we still can't do it because we don't have the technology to do it except for neutrino oscillations. So it stands to reason, and this is not a physics statement, but it's sort of a broad logic statement, that it's probably a good idea to do more neutrino oscillation experiments because we can. And I will say that there's a whole bunch of fascinating, unique, beyond the standard model physics you can do with all other kinds of neutrino experiments. And I will say absolutely nothing about any of them, except for writing them down here. So if neutrinos have mass, what else can they do? And they can do lots and lots of different things. And those are the sorts of things that neutrino oscillation experiments can inform. For example, there could be more neutrinos, and Mark already alluded to that. You can complain, why would there be more neutrinos? The first answer is why not? They're nice, they don't screw anything up, and they may have something to do with why neutrino masses are not zero. Neutrinos might have new weak interactions. That also changes the way in which they oscillate. Neutrinos have other properties because they have mass. We know, for example, that the heavy neutrinos decay. They don't have a choice, they have to. Their lifetimes are like 10 to the 30 years if there are no interactions beyond the standard model, but they decay. They might beat the protons, but that's it. And neutrinos also have a non-zero magnetic moment because they have mass and because they couple via the weak interactions. And these phenomena are impossible to observe unless you have more new physics. But if they do happen, they could impact the way in which we do neutrino experiments. Neutrino oscillations are very interesting. As Mark pointed out, it's a quantum interference device with a ridiculously long baseline. So the coherence length is also kind of ridiculous. Before people complain, that's actually cheating, because in the neutrinos clock, everything is super fast. But we don't live in the neutrinos clock, we live in this world. So we have coherence lengths that are hundreds of kilometers or something like that, if I use the right definition of coherence length. Okay, so I'm going to talk about two examples very briefly. What happens if there's an extra neutrino, which is what Mark talked about? And again, it's a very easy way of expanding the standard model. Nothing bad happens. And what happens is, depending on the masses of your extra neutrino mass eigenstates, you get a whole bunch of new mixing angles that you have to memorize. So I'll leave this up here for a few minutes. I want to point out that the most exciting thing that comes out of this is that you have new sources of CP violation, for example. And if you have one of these stereoneutrinos, and if you pick a nice one, this is what nu E appearance at Dune could look like. And what's important here is that you get this extra oscillation frequency on top of the one that we know about. So that would be kind of amazing if we did an experiment like that and that happened. Okay, so it's a very robust signature that you could see at Dune. And of course, I picked the right point for this to be nice, but nonetheless, Mark showed you the sensitivity region for Dune. So I want to show you what happens if you get lucky. And you could be in a world where you actually get to measure these new mixing parameters. And I picked them to be very small because they're already constrained by experiments we've done so far. So this is regional parameter space that's allowed. And on top of that, what's more exciting is you have these etas. These are the CP violating phases. So it is also possible that you can determine not only that CP is violated in the neutrino sector, but that there's more than one source of CP violation. So that would be great. And this is the kind of physics we could run into. We don't have to, so always keep that in mind. But it's interesting. And tau appearance also adds information that's non-trivial that you can't get anywhere else. The other scenario I want to talk about is that maybe the neutrinos have a new weaker than weak interaction that I can parameterize via dimension 6 operator. They're all different types of dimension 6 operators that I can write involving neutrinos. If I write a neutral current one thing that it does is that it changes how neutrinos propagate via matter effects. So we like to parameterize this in this way to make everything look like a non-relativistic quantum mechanics because we understand how to do that. And we can place a whole bunch of bounds on these new interactions, or maybe we can make a discovery that there's some new interaction. Let me make a very quick parenthesis because people complain about this a lot. How can the neutrinos have a new interaction and we not know about it? Haven't we been doing all these experiments with charged fermions and quarks and all of that? It looks unlikely that that can happen. So here I'm asking if it is possible for you to construct a model where you have a large non-standard interaction that would show up in a neutrino experiment, and whether that model is good for anything. So that's a question that people often ask. And here's the answer, yes and yes. And we can talk about it later if you want. Non-standard neutrino interactions are also interesting because they have new sources of CP violation. These are harder to picture because it's a matter effect. Matter effects already violate CPT because the background has only electrons in it. So we illustrated that by calculating an oscillation probability at Dune. This is a standard oscillations as a function of energy. The gray curve is oscillations with the non-standard interaction, but CP is conserved. And then I have two curves. In the gray curve, I have two curves on top of each other. And this is not CP violation, but it's T violation. It's the nu E to nu mu versus nu mu to nu E. And you can see that when there's no CP violation in the non-standard interaction, nu mu to nu E and nu E to nu mu sit on top of each other. If there's CP violation, you get this huge T violation. So there are new sources of CP violation that you can tease out by doing the Dune experiment, for example. I'm not going to show you the sensitivity plots because they're always super boring. I do want to show you an interesting thing that we can do, which we did in this paper a very long time ago, is that we simulated Dune data, assuming that there's a non-standard interaction. But then we analyzed the data, assuming that there's a fourth neutrino, a stereoneutrino. And not surprisingly, we got a good fit. It's a weird fit, so don't stare at it for too long. But it means that if you find new physics, you'll be super happy. But then the next step is to figure out what the new physics is. So how do we do that? There are lots of things that can help you. And one thing that can help you in particular is we're doing two experiments, Hyper-K and Dune. They have the same kind of L over E, which is the neutrino clock, if you want to think about it that way, because you need to wait enough time in the neutrino's rest frame. But they have different L and E. So there are some kinds of new physics that like to behave like L over E, but some kinds of new physics don't. So by comparing, for example, Hyper-K and Dune, not only can you find new physics, but you might get a lot more information about what the new physics could be. Of course, you can combine very different data sets, or you can also combine lots of different oscillation channels. So you can look for new mu to new e, and then new mu to new mu, new mu to new tau. And if the story holds together for a particular new physics model, it may not hold together for a different new physics model. So here, for example, is a function, new mu to new e is a function of L over E for the hyper K baseline and for the Dune baseline. And the bottom line is in hyper K, the non-standard interaction still looks pretty oscillatory and well-behaved as a function of L over E. In Dune, it looks really weird. It looks like that because matter effects are very strong. So if you're measuring subsets of these L over E ranges in these two different types of baselines, you might be in business. So let me change gears and talk very briefly about why neutrinos are a great source to look for new particles, in particular dark sector particles. This is a reminder of how a neutrino beam is made. You get a bunch of mesons, pi pluses decay into new mu's. Those are your new mu's. You also have these pi zeros that are good for nothing, but they're there. And if you think about new physics, the pi plus could decay into some other fermion. And the pi zero could decay into some other photon, like a dark photon. And these things, the photon and the new fermion, they could show up in your detector either by making it all the way there or by decaying into something else that will then make it all the way there. And then once they find your near detector, they might hit something or they might decay. So you have a great place to look for all of these very, very shy particles that are hard to produce, but we're producing a lot of pions and a lot of pi zeros that are good for nothing, but these interesting things can happen. And then there are all the other mesons as well. I only want to show one plot, and the one I found is kind of bad, but nonetheless, it's a good plot, but the colors are weird. So this is what happens if you look for a new neutrino, a new heavy neutrino. It's not really the stereo neutrino that you show up by oscillations because it's too heavy, but it's kind of the same in spirit. And the current region in white is ruled out. The sensitivity of different neutrino experiments in the future is highlighted here. What I want to highlight is the fact that there's this band over here called type 1. Okay, and this is what the type 1 seesaw predicts. So if the right-handed neutrino masses are in this sub-GeV range, there's a prediction for the new mixing parameters, and that prediction lives over here. And you see that the Dune experiment, if everything works really well, it can actually touch this line. So here's a way in which you can rule out a neutrino mass generating model by doing a neutrino experiment. And we don't know other ways of doing that if the parameter range is over here. Now keep in mind, the mass range goes from EV to ZeV. So this is a tiny sliver of that parameter space, but I think it's super exciting. So finally, the last thing I want to tell you about is we may already be sitting on new physics beyond the standard model in the neutrino sector. The key word here is might. We don't know. But there are some things we don't understand. There's the old LSND anomaly. It's still unresolved. We're pretty sure the data are good, but it doesn't fit into our understanding of neutrinos. There's a mini boon data. Also, there's an excess of events that's also not understood. And we're working on that. On different fronts, there's something called the reactor anomaly. It also sees what we don't expect to see. It also sees this weird spectrum here, and I'm not going to talk about this at all, but we've made a lot of progress in understanding this anomaly, and it's probably not physics beyond the standard model. It might be that there's some beta decays that we're not describing very well. Again, there's still a lot of work to be done, but progress has been made. And then there's this thing called the gallium anomaly. This is the result of the BEST experiment, and they see a huge depletion relative to expectations. And if you combine with the previous gallium anomaly, this is about a 5 sigma effect. Again, these experiments know what they're doing. This is not an statistical fluke. It just means that either we're not understanding these sources particularly well, life might be complicated, but all of these things need to be addressed. And we're working on that. We have been working on that for a long time, but there's now dedicated programs towards trying to figure out what's going on here. For example, the microboon experiment has gotten to be very popular. Oh, I forgot. So this is what I want to say about this. There are lots of new theory ideas that try to address subsets of these anomalies. So we've gone way beyond just postulating that there's a stereoneutrino, partially because the stereoneutrino solution doesn't work very well, depending on who you ask. If you ask me, I don't think it works at all. But there are all these theory ideas, and you shouldn't be surprised because that's what theorists do. But I do want to highlight the fact that these theory ideas are very important for the experiments because they provide opportunities for new searches that the experiments can do. They also guide how experiments get set up. And for example, in the case of a microboon, they have led people to not just look for electrons and photons, but to actually look at more complicated final states, because the new physics could be, instead of either an electron or a photon, it could be any plus and minus pair. And microboon has been working on how to do that. And of course, you can ask in hindsight, why didn't they think of that before? But that's how life works. So there's a lot of stuff I'm not going to talk about. A lot of it is here in this slide. And this is only stuff that's mostly related to neutrino oscillation experiments. So there's a whole wealth of physics that you can look at this. So let me summarize with my main ideas that I said before. Neutrino masses are beyond the standard model we know. We know very, very little about this physics. Neutrino experiments can help, but they don't have to. So you have to do the experiment in order to find out. It is possible to run into more new physics in the neutrino sector. Massive neutrinos are interesting because they can do more things. Neutrino oscillations is interesting because you can look for new states and you can look for new interactions as well. Neutrino experiments are a great place to look for beyond the standard model physics, especially of the light variety and especially of the very weakly coupled variety. So we've just begun exploring that in detail, and there's a lot of work to be done there. There are some technical challenges that are very important to appreciate. You can only look for new physics in a near detector setup if you have a good near detector setup with the right detectors, and if you understand neutrino scattering very well. Otherwise, you're going to confuse new physics with neutrino scattering that you don't understand very well. And finally, it is possible that we're already sitting on a lot of new physics or more new physics in the neutrino sector, and we don't know what the answer is. But we're working on it. And we expect a lot of progress in the next 5 to 10 years. And if we're lucky is the operative word here, that will be resolved. And we might either be happier because we understand things better, or we might be in a world where our questions are going to evolve in a qualitative way. So I'll stop here. Thank you.
Thank you, Andrew. Next up is Kate Scholberg speaking about astrophysical neutrinos.
Yes, sir.
All right. Okay, so I'm going to tell you about neutrinos and astrophysics. So neutrinos are everywhere. They pervade the universe. So what this is here is a plot of, is this working? There we go. This is a plot of the flux of neutrinos from natural sources over all the energies that we know about. And one reason to look for them is that detecting them will give us information about these sources themselves. And so here's a bunch of these sources here. The virtues of neutrinos, the blessing from neutrinos is that the information can come out from very deep inside astronomical objects, exotic ones, and perhaps more mundane ones, including the Earth as an astrophysical object. Furthermore, the neutrinos are unperturbed by matter to a good approximation and by electromagnetic fields, so they point back to where they came from. This is thanks to the weakness of the interaction, but they are, the curse part is that the weakness of the interaction also means that the neutrinos are very, very hard to detect. In turn, neutrinos certainly give us information about the objects, but they also give us, they are nice big old sources. These objects are sources that, that give us information on neutrinos themselves and on physics, you can learn about 3 flavor oscillations. There's anomalies that Andre just talked about, and many, many, many opportunities for beyond the standard model searches. And this is a really nice graphic that I took from this SNOMES white paper. It was focused more on high energies, but it's really true for all neutrino energies. The observables you have a handle on in your detector are the neutrino energy, the direction the neutrino came from, in many cases, the time that you measure it, and the flavor of the neutrino. And there are many interesting signatures of BSM physics acting either production during propagation or at detection that will you can learn about. You can probe these models by measuring these observables. I must also point out, and Andre also alluded to this, that it's not only neutrino sector physics that you can learn about in neutrino detectors. If you have neutrino detectors, you can also search for new physics in other sectors, and I'll show a couple of examples of those. And you have to point out that the neutrinos from natural sources are free. You just have to look up or also look down for neutrinos. You don't care whether it's up or down. Just depends where the source is. And it's really, it's like, so the catch is you actually need to build a detector. And it's kind of a good deal because, for example, if you want a cell phone plan, you know, often you get the cell phone for free or for cheap, and then you have to pay this monthly subscription. For astrophysical neutrinos, it's a better deal because it's like you only have to buy the phone and then you get the monthly subscription forever. You know, you might have to upgrade the phone occasionally, but it's really, you know, it's overall, I think that's a better deal. And this information that comes from neutrinos is over enormous range of energies, over 25 orders of magnitude in energy in this plot. And the region, I just want to point out, the region over which we have now directly detected neutrinos is in this range. And so there's really a lot at the edges of this range where nobody has ever directly detected any neutrinos. Here's another nice plot that I stole from this that same white paper, which shows neutrino energy and also puts it in terms of travel distance and puts the names of many, many experiments that are going after these neutrinos from natural sources, existing and proposed. I, of course, cannot go through all of these examples. Then if you expand your horizon to multi-messenger astrophysics, neutrinos are really only one messenger. There's also, in the wider field of astrophysics, there are charged particles and cosmic rays. Gravitational waves, of course, is an entire new kind of astronomy. And photons, of course, over the whole spectrum. And information from natural sources and also BSM in both ways will come from a combination of these sources. And so this leads me to the standard disclaimer. We have so many experiments. Even if you're just thinking of neutrino astrophysics, it's like having an enormous library of very nice craft beers. The multi-messenger astronomy is like having a well-stocked bar with all kinds of different drinks. But of course, it would be a bad idea to drink all of these at one sitting. And so what I'm going to do is just go through a few chosen examples. There's details, a lot more details in the NF reports. So I'm going to start here with my examples at the high energy end here for the ultra high energy neutrinos, and what you consider high energy and ultra high energy really depends a bit on your on the particular community. There are multiple kinds of detectors going after this very high energy N greater than TeV, and going up to PeV, EeV, and ZeV. And these come in different types. There are long string water Cherenkov detectors like IceCube and KM3Net. There's detectors that are either balloon or in ice that are based on electromagnetic antennas. There are also cosmic ray shower detectors that are located either on the ground or in space that also have sensitivity to very high energy neutrinos. Here's just the example I pulled out is the fabulously, whoops, sorry about that, go back. Yep. The fabulously successful IceCube at the South Pole. This is just one pulled out success of this, a multi-messenger detection of a enormously energetic neutrino, possible, it's unclear what the source is, but possible active galactic nucleus. This is where it looks, I guess you can't quite see, but where it looks on the sky, where IceCube, of course, also looks for diffuse sources of neutrinos. And the kind of ultimate goal of the ultra high energy neutrino experiments, or one of them, is to really go for what are known as cosmogenic neutrinos. These are neutrinos that originate from charged particles scattering off the cosmic microwave background, where you get hadrons. These also result in photons, but the hadrons decay to give you neutrinos, which would be in this really extremely high energy range. And there are actually multiple programs, including the detectors I showed you, going after these. Now going down a little bit lower in energy, so the GeV to TeV scale, this area is, this range of energies is inhabited by mostly atmospheric neutrinos, but also possibly some other more exotic sources. And there are multiple detector technologies in use and proposed for observing these kind of neutrinos in this range. There's water Cherenkov detectors. This has the advantage of really proven at very large scale. We heard already in Mark's talk about those. There are trackers, so like NOVA and MINOS, with good particle reconstruction. And then, of course, liquid argon time projection chambers like DUNE with really, the word is always exquisite, really fine-grained particle reconstruction. And so these detectors have their day job is current day job is looking for long baseline neutrinos that are produced artificially by accelerators. So that's what we heard about from Mark, the current generation being NOVA and T2K. But these are fantastic detectors of natural neutrinos too. And of course, in fact, the Super K detector made the original atmospheric neutrino oscillation measurement, making use of the free natural beam from cosmic ray showers. For the next generation, there's Hyper K and DUNE. And of course, you've heard a ton already about DUNE and also about Hyper K in Mark's talk. I want to emphasize that these detectors, although their day job is the long baseline neutrinos, they really are multi-purpose and have very broad physics programs, including many different sources of astrophysical neutrinos, not only GeV range, but also lower, as I'll get to in my next energy step down. And here's my next energy step down. And actually, this region is the one that is my personal favorite. That's just where I spend a lot of my time. This is the few MeV to 100 MeV or so scale. And the sources that inhabit this regime, sorry, this keeps happening. Sources that inhabit this regime are solar neutrinos, also involved in Nobel Prize shenanigans, and neutrinos coming from the Earth and from supernovae. And I will briefly talk about some of these technologies, and some of these are the same as what we just talked about for higher energy neutrinos. So there's the water Cherenkov detectors and liquid argon TPCs. But in this regime, there's especially nice sensitivity to astrophysical neutrinos from liquid scintillator, where here, comparing some of the virtues of these different kinds of detector technologies, water Cherenkov is cheap and large. There's a nice directionality from the Cherenkov ring. However, it has typically rather low light yield. If you compare that to liquid scintillator, you can get a lot of light, enormous number of photons for energy deposition, and so that gets low threshold and good energy resolution. Directionality tends to be not as good. And I can point out here that there's actually been quite a bit of progress in trying to marry the best properties of each of these detectors in actually literally mixing water and liquid scintillator to make hybrid Cherenkov and scintillation detectors. And so there's actually some exciting new progress in that regime. And then for liquid argon TPCs, these also have the dynamic range to go down to a few MeV scale and can make use of the ionization, which is typically drifts and is therefore a bit slow. But scintillation light in argon is fast and can also be gathered. And the directionality of this kind of detector is good. It's a tracker. In general, these are limited by efficiency, just not having enough energy deposition. That's the challenge at very low energy. But a worse challenge is the background. And so this is a different set of challenges than the GeV scale detectors. Let me zoom in a little bit on one application, which is my favorite one here, is neutrinos from core collapse supernovae. This is the incredibly intense burst that you get. It basically almost all of the binding energy of a neutron star that forms from the collapse of the core of a star at the end of its life. Almost all of that binding energy is turned into neutrinos of all flavors in a very short time period over about 10 seconds. It's mostly nu bar pairs from the cooling of the star. And the time scale is something like maybe a few tens of seconds, and you get all the flavors here. This is just a nice pretty picture simulation. And so if you look at it on this flux plot, this DSMB is diffuse supernova neutrino background. And what a burst supernova is, it's like this piece of the spectrum just springs up something like 9 or 10 orders of magnitude for a very short time period of about 10 seconds. And so it's really a very sharp and intense burst. Many of the detectors I talked about, in fact, I think almost all of them so far, are sensitive as well to bursts of supernova neutrinos. And the thing to take away here, so there's a lot of different kinds of detectors, including the Water-Cherenkov scintillator and argon. The takeaway message here is that these have different flavor sensitivities. Some of them are primarily sensitive via inverse beta decay on protons to nu E bar. Argon is sensitive to nu E, the electron flavor. Also, I'll say a little bit about that later. Dark matter detectors, for example, large and noble liquids, are sensitive to all of the flavors via coherent elastic scattering on nuclei. And the next generation big detectors will all be absolutely fabulous supernova detectors. So Hyper K will have the order of 100,000 events for a supernova at the center of the galaxy. Juno, 10,000-ish. Dune, probably about 3,000. But the takeaway message here, the important thing to know is that the flavor sensitivities are different. The scintillator and water, because there's free protons, are sensitive to nu E bar. Dune is sensitive to electron neutrinos, and this really means an extreme complementarity between these two different kinds of detectors. It's not a competition at all. It's the kind of thing you want all the information you can possibly get. You really want all the flavors. You want as much as possible, much information as possible from a really rare burst. And this is actually kind of a general feature of multi-messenger astronomy. The more you have, the better off you are scientifically from not only neutrinos, but other kinds of signals. And so this is just an example of the time scale of what you expect from a core collapse supernova. You expect gravitational waves, electromagnetic signal late, and neutrinos. Here's an example of a network. This is supernova early warning system, which is designed to give an early warning, a high confidence prompt alert of a supernova, which the idea is really to enable the maximum possible physics and astrophysics from a supernova burst, which is only expected every few decades. Okay. Now, I want to make a comment here that dark matter detectors, there's many connections with other frontiers here with neutrino physics and the cosmic frontier, for example. I have to thank the CFO1 people for some help with this plot. So this is the standard particle dark matter kind of plot where you have one axis, which is the coupling, and another, which is the dark matter mass. And here's where you're sensitive with direct detection experiments, very deep, clean, sensitive to very low energy recoils. And looming and threatening down here is what's called the, used to be called the neutrino floor. It now seems to be more popular to call it the neutrino fog. This is the parameter space region where if your detector is sensitive to those parameters, it will be in fact blinded by natural neutrinos causing coherent elastic scatters in the detectors, which are neutrinos that just come in and smack a nucleus, and you get a little recoil that looks exactly like a dark matter detector, again, and dark matter bump, and can only really be disentangled statistically rather than event by event. And so that's the neutrino fog. But I think it's important to recognize that the neutrino fog is actually potentially a signal as well. There may be actually very interesting things emerging from the fog. In fact, if you break it down, here's a nice paper from Kieran O'Hare showing, this is the same kind of thing. This is what used to be called the floors, now the fog, and you see there's all this potentially interesting signals from natural neutrinos that will eventually emerge if the detectors get sensitive to those dark matter parameter in that regime of those dark matter parameters. Okay, now to finish, I just want to go to the very lowest energy end here. So down in this region here, you have the cosmic neutrino background. So the neutrinos left over after the Big Bang. So there's actually lots of them. It's a high flux, but it's very low, very, very low energy, very hard to detect. We actually have detected them indirectly using a combination of multiple cosmological observables. And so I've stolen these slides from Yvonne Wang, who gave a very nice snow mass neutrino colloquium on this topic. There are many observables in cosmology, and the combination of them, you get a fit where you can learn about the absolute mass scale. The observables are sensitive to the sum of the neutrino masses and also the number of neutrino families. And so these are the main neutrino inferables. And at face value, it's actually very impressive. The limit here from the current data is quite a bit smaller than the best terrestrial measurement or limit on the sum of the neutrino masses. And the number of neutrino families is consistent with 3. It doesn't quite rule out more than that, but it's really looking like 3. And so this is really very, very good information using lots and lots of pieces of information put together. And there's actually very good prospects for the future for various cosmology experiments. And it may be possible to go down to really where we expect we really have to see some kind of neutrino mass. And I want to make the point, and I'm not going to go into the details of this slide. This is another slide from Yvonne's talk. But the key thing is that these are fits to different kinds of cosmological parameters in addition to the ones from neutrinos. The more information we have from the laboratory about neutrinos, the better we can constrain cosmological parameters. And so this is, in one direction, the cosmological measurements will tell us about the neutrino properties. But if we can learn about neutrino properties, mass ordering, absolute mass scale, sterile neutrinos, then that gives input into the cosmological fits. And let me just say one more thing. This is my last example. This is the idea of trying to go after the direct detection of the cosmic neutrino background. This is something that is very, 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 very hard. I put the holy grail up here since this is something, I think it said that every experimentalist spends some time trying to think about how would you actually do this. There's a lot of ideas. Few of them seem very promising. The best possibility so far seems to be something called zero threshold reactions. It's basically absorption on radioactive nuclei. If you have standard inverse beta decay, then there's a kinematic threshold. But if you have a radioactive nucleus, the energy is available for the interaction to go. And this would manifest itself, for example, in an endpoint of a tritium spectrum as a little bump separated from the endpoint. But what you need is absolutely unimaginably good energy resolution to see that. That hasn't deterred some experimentalists who are going after this. And there's actually recently been some technical progress on that. Okay, so my final comment, those were examples, not at all comprehensive, just a sampling. But I want to comment here just in general that when you're measuring neutrinos, and so you're measuring an event rate, and here I have it as a function of energy, but in fact, there's other observables for astronomy. There's also time and direction, but here just pulling out the energy response. So you measure a spectrum of events as a function of energy, differential spectrum as a function of energy, and that is a convolution of the flux, so basically the source, and this will be for a given flavor. There's a cross section and a distribution of interaction products. So this together a differential cross section, and of course a detector response, which is maybe mundane, but you do have to understand your detectors. And new physics can lurk in different parts of this convolution. You can have new physics, and this goes back to that diagram I showed you before as well. There can be new physics that's in the source and new physics that's in the propagation as well, and that would show up here in this flux. There could be new physics in the interaction as well, and that will show up here. I hope there's no physics in the detector response, but of course you never know. But my point here is that if you have a signal and you're looking, you have a measured observed distribution, if you want to interpret that in terms of physics, you need to understand all the pieces, and you really need experiments. It may be that we need extra experiments to understand the cross sections, for example. You know, it's not just one measurement. It really is to learn about nature. You need multiple experiments to understand all the pieces of the puzzle. Okay, so this is my last slide. So here's the takeaway message. And so this is my favorite thing to do these days, which is to use AI to make images. And so this was probably can't read that, but I think I plugged into the AI image generator something like catching rain in multiple buckets and somebody dancing in a raincoat with a cup to catch the rain or something like that. And it came up with this. Really the point here is that neutrinos, they're messengers of astrophysics. And especially in that context, you know, they're telling us deep inside what's happening deep inside objects. They're giving us really unique kind of information. And this is really not a competition. We really want to catch as many of them as we can. We want to have our buckets, as many buckets and as wide buckets as we can that are distributed around the whole field here. It's really, you know, it's you know, not a who's going to do it first. We all want to get the neutrinos. And they're messengers of physics as well. And I guess, you know, this statement also applies there as well. And the sources are free. And really, it's an enormous range of sensitivity to new things that we get by opening our eyes to these neutrinos or opening our buckets. And really, this whole field has just so many interconnections, not only between frontiers, but also outside particle physics, and really is most effective science is going to come out by having a broad program across scales and many connections. So I will stop there.
So for the question session, I'd like to ask the speakers on stage. They have nice chairs for you. So you don't have to stand. And if we can bring up the first slide again.
How possible it is to hear.
Manage that.
Yes.
And the second.
Pass this around.
All right, and while we're taking all our seats, so all this exciting physics, of course, also translates into a message where we want to go in the future. And so this here is I'm just going to read the bold text for you. So we'd like to have a future program with a healthy breadth and balance of physics topics, experiment sizes, and timescales supported by a dedicated, deliberate, and ongoing funding process. Of course, the completion of existing experiments and execution of DUNE in its full scope are critical for addressing the NF science drivers. There are some opportunities presented by the DUNE Phase 2 program, and to exploit these new opportunities, we need directed R&D to find out what kind of new detectors we could put into these DUNE caverns. We need strong and continued support for neutrino theory is needed, and of course, this is not driving our budget, but it's still very important that it happens. And we believe there are unique opportunities for Neutrino Frontier to contribute to leadership of a cohesive HEP-wide strategic approach to DEI and community engagement, which is urgently needed. And with those remarks, I'd like to open this up for questions to any one of the three speakers. Thanks. All right, questions? There in the middle. Take this one.
So this is a question for Andres' talk. You highlighted the importance of having two experiments to distinguish this NSI. So I was wondering what happens if you just put current data, like T2K and NOVA, and try to see these NSI as things just overlap, or we're not sensitive enough, or we're not seeing anything. Probably it's helpful if people look at the slide. I don't know if it's possible to bring it up. But.
Yeah, so let me answer what I think the question was. And you're talking about T2K and NOVA and the fact that we already have a situation like that. We can take it one step further. Actually, T2K and NOVA have this, in many quotes, a discrepancy. And one question is, would NSIs help resolve the discrepancy? The answer is not a lot. People have done the analysis. I can preempt the next question, which is, would a stereoneutrino help? The answer is not a lot. People have also done the analysis. So, but I think this is a good example of the kind of breadth that you get by having two detectors that are quite different. You know, the technologies are different. Their approach to controlling systematics is different. The L's are different and the E's are different. First of all, if they agree, you trust your result more. If they don't agree, you worry about whether you understand your systematics very well. And if you convince yourself that you do that, then you can look for new physics. And I think that Dune and Hyper-K is a version of that at a time when we're aiming at high precision. And I think all of those things will be very important. I hope that was part of the question.
No, I was just wondering what if you do a plot like the one you showed in the paper?
Oh,
When you just put, T2K and Nova and try to see these NSI, because I was just wondering whether you get indeed this kind of discrepancy or the error bars are such that you can't really tell whether there's a difference.
So there are circumstances where they would be able to tell, but in general, given the constraints that we already have, they're not as it's not as big an effect as you can see with Hyper-K and Dune.
I see. Thank you.
Question from Zoom. Okay. Yeah, go ahead. Uday.
Oh, yeah, thanks. So yeah, this is just a question for regarding the neutrino fog. And I think this is a new terminology that we created and probably during the SNOMES process. And there are like people from other frontiers in the audience. So maybe we could explain a little bit more what the meaning of that is and how do we use it in the scientific context? Yeah, thanks.
I'm not sure I caught, excuse me, I'm not sure I caught all the questions. The question was about the neutrino fog. And
Yeah, just in general, like how do we understand it? And because I think this was the neutrino floor, right? But
yeah,
now
right.
we use a new terminology. I just don't know if people in other frontier would know the context or the meaning of the neutrino fog.
Right, yeah, so how do we understand it? So one possibility, which I didn't actually mention specifically, is directional detectors. So if you have detectors that have the capability to observe the direction of nuclear recoils, that is actually an extremely strong handle on disambiguating a statistical signal that comes from an astrophysical source like the sun, or for example, a WIMP wind, dark matter. So that's kind of the most obvious answer for how to pull signals out of the fog is by adding the observable of directionality.
I see. Thanks.
So Andres and everyone, thank you very much for very interesting presentations. Andrea, in your talk, you mentioned something which we are not often talk about, and that's neutrino decay. So can you say a few words about that? So how it could help us to understand nature of the neutrinos?
So again, the sound here is really horrible. So keep that in mind. So you're asking about neutrino decay. And
how it could help us to understand nature of the neutrinos.
Very good. So, just to repeat the statement that I made, the neutrinos definitely decay just because of the standard model. We don't expect any of our neutrinos to ever decay in an experiment because the lifetime is too long. So if you could measure a lifetime for the neutrino, that would have to be mediated by some new interaction. So this is it's a cheap way of finding some new interaction if you just want to think about it that way. There's an entertaining factor about neutrino decay, which is if you only restrict yourself to laboratory bounds or even solar neutrinos, the bounds on the neutrino decay are like milliseconds. So you have a prediction that's 10 to the 40 years, and your bound is a millisecond. So there's a lot of room to look for more phenomena. It's interesting if you're a theorist to ask, can I write down a model where the neutrino would decay fast enough that I can see it and that the model is not ridiculously ruled out? The answer is you can do it. The simplest kind of models that you can write down are probably when the neutrinos are Dirac, because if the neutrinos are Dirac, I can write down a decay that looks like the Fermi operator, except that they're only right-handed neutrinos, for example. Good luck constraining that with another experiment. But yeah, and finally, the last thing is neutrino decay is a textbook example of how to modify oscillations. because you're adding another L over E effect because of relativity, but it does that in a way that you would not be confused as long as you have the ability to see wiggles, because the decay doesn't oscillate. So I hope that that addresses your question.
All right. Do we have something online? Okay, then I think over there.
So Andre and Mark both discussed a lot of interesting things. I think Andre, especially with this neutrino BSM, but it really depends on the ability to do precision experiments. And there are limitations to the precision that you can have in neutrino physics if you use few GeV neutrinos, because our understanding of low energy hadron physics is just not very good. So for example, in the mini-Boone anomaly, it's not seen at high energy. It's only seen in the region where we don't know how to compute the neutrino inelastic cross-sections. For Dune, this is a problem because we don't have generators that describe the inelastic neutrino cross-sections. The current generators sometimes are wrong by 50% in some regions. And the kind of zeros that Mark talked about can be filled in if you have poor energy resolution in the neutrino energy. So for both programs, what are you going to do about this when we actually come to the experiments, see anomalies, and have this question about them?
Thanks for the question. So I think a lot of that hinges on the near detector, and one normalizes what one sees at the far detector to what one sees in the near detector. And so if you have a good near detector that can cover all of the kinematic phase space of your far detector, and the detection efficiency is high, then you don't actually need to know the neutrino cross-section that well, because it is the same near and far after you've controlled for flux differences and all of that. Now, to really get to precision though, the argument I just gave you sort of works at first order, and I think we really need sort of the second order, correction. And so you really do want to do the work of, test beams, measuring the response of your detector to, individual hadrons and final states. You want to do the work of hadron production experiments so that you understand neutrino fluxes that you can then divide out. But I think it's really, it puts an onus on building the best near detector that you can to get to the kind of precision that we're talking about.
Can I add something? And you're completely right, but I do want to highlight the fact that some of the observables that I talked about are quite robust in the sense that they give you a kind of feature that would not be fooled by mismodeling neutrino interactions, for example. But what you said is completely true, and it just means that we have a lot of work to do in order to do a precision neutrino experiment. It's not just having the great beam, the great detector. We need a great theory, and we need a lot of data in order to constrain these interactions, because they're hard, as you pointed out. But we know how to do it, hopefully. Or I don't know how to do it, but these people know how to do it.
On Zoom, Mary?
Yeah, I mean, I had a comment to follow up on some of the earlier questions about, the NSIs and resolving this T2K and hyper K. So for the non-neutrino physicist, one feature of both T2K and NOVA is they both sit at the maxima of nu mu to nu e oscillation. So they only sample a small part of the interference. The next generation detectors like hyper K and Dune. So hyper K has the advantage also compared to the current generation of 10 times more statistics. We're talking thousands of events, in terms of nu e appearance compared to the 20, 30, 40 we may have now. And Dune has the advantage of covering a large fraction of the oscillation pattern, almost, one peak, one dip, and almost a second peak as well. And so both of these, you get the statistical power from hyper K, and you get shape information from Dune. Eventually, if you add statistics, then that shape information gives you, it's an interferometer, right? So the bandwidth and the length are important. And so that's a subtlety that's why these next generation experiments, of course, we have large bandwidth from atmospheric neutrinos, but you don't always know very well what the baseline is. And so you don't know what the interference pattern, actually underlying interference pattern can be from there. But that is also another piece of information that allows us to try and discern the different physics models that are coming in from the measurements, both with the beams and which offer very good accuracy. We expect with the current measurements, engineering measurements that are going in, that we would be able to model the neutrino beams to about 5% is the limitation that we're aiming for in this next generation experiment. Thank you.
Thanks for that comment. Over here.
Okay, thank you for the presentations. A nice overview of what's going on, and all of that supports the neutrino frontier message that was briefly flashed. There was one piece of the message that wasn't explicitly addressed in the talks, that there are unique opportunities for the neutrino frontier to contribute to the leadership of a cohesive HEP-wide strategic approach to DEI and community engagement. Can you tell us a bit more about what's unique that the neutrino frontier can provide here?
Yeah, I mean, yeah, yes, we did. So you want to take it? No. Okay. Yeah, I mean, I think given the really high profile role of neutrino physics in the US, I think that gives the community a great opportunity to, take leadership. And really there's already, in fact, I think there's a session tomorrow on success stories in the neutrino frontier. I mean, obviously there's much more work to do, but I think that's really what we mean is that we should seize the opportunities that we have as a really strong program in the US.
So maybe if I may chime in also specifically, we are now in neutrino physics approaching finally the sort of the large collaboration scale. So we start to have collaborations with more than 10 to the 3 members. But we haven't been doing this for 20 years or so. So I think we have a chance in forming these large collaborations to really explore new ways of right from the start getting DIA right and not sort of do this as an afterthought. And I think it's really, neutrino physics was for a long period, very small experiments, right? And so where the small experiments tend to have a lot of this formalized structures. And so since we have to create a lot of these structures, and Dune is already in the process of doing this, I think, given that we're doing this at this time where DIA has such a high profile, I think we really have the chance to be creative and explore new ways to really do something about that. But at the same time, we cannot do this without the partnership of everybody else in HEP.
Right. I mean, I think neutrino physics is not special in the need for DEI. I mean, that's, I think, universal in the entire community. But I think we should take advantage of what we can. And it goes along, I think, a bit with the breadth of the connections and the physics. I think that also offers opportunities to enable even, greater training opportunities, greater outreach opportunities, and so on.
Maybe I'll just add one item to that, which is I think it's a reflection of what we've heard from the members of our community, and particularly the early career members.
Yep.
And I think in the energy, in the neutrino frontier, and I'm sure also in the energy frontier, we're very fortunate that we have a number of early career members who have brought these issues to the fore and pointed in the directions that we can make positive improvements.
Do we have any questions online?
There's a question all the way in the back.
Okay,
Sorry.
very good.
Yeah, so I should preface this by saying I'm not part of the neutrino frontier. Okay, can you hear me now? Okay, so I should preface this by saying I'm not part of the neutrino frontier, and this is truly a naive question. I was chatting with like a neutrino physicist throughout the week who said, I just really want to measure delta CP. And as someone who should probably know we should probably know the physics of like what does measuring delta CP and the mass ordering tell us about the universe and beyond the standard model physics, right? Like this is sort of the first part of the question. And then I think it was Mark's talk had slide 24 where you have like delta CP and some specific BSM models that you're you're trying to map that potential value onto. Can we like make quantitative statements based on what phase 1 dune will measure and phase 2 dune will measure in terms of precision of delta CP and mass ordering and what that means for our understanding of the universe?
I would say that all very detailed quantitative things you can find in the Neutrino Frontier report. There are tons of plots on that, but who wants to take it? It's sort of two-stage question, so who wants to take it?
Well, delta CP is not all I want to measure, but that's that would be really it would be great to be able to do that. I think the answer for me at least has kind of two parts. We do want to measure delta CP, and if you look at the next generation of experiments, I think the precision in sort of the worst case is something like 7 degrees or something like this. But I would have to look at the plots to really understand that. And if you looked at that that plot, it was cosine at -1 on one side and +1, so it spanned the whole range. And so I think you really are going to have some discerning power in that next generation. What I think gets me personally excited is that once we're able to sort of finish the PMNS and measuring delta CP as part of that, we're doing something really powerful. We're measuring neutrino oscillations extremely precisely. And then that becomes, a springboard for looking to see what else neutrinos maybe talk to, what new physics there is. And so, yes, I think, I personally am interested in the delta CP measurement, but I think I'm even more excited about what comes next.
There's no right answer to this question, but I think everybody agrees that it's very, very important to look for CP violation in the lepton sector. And I think there are different angles you can take at this. I think what Mark is saying is we don't just want to measure these parameters, we want to measure them a lot. And the reason we want to do that, or the reason we have to do that, is that we need to make sure that this nice picture that Mark showed is actually the right picture. That's usually how physics goes, right? I mean, you're not satisfied with just measuring the parameters in the way that we've gotten here so far. We really have to be in a position to be able to test non-trivially if we have the right picture. I think a very completely different angle that we should always keep in mind as a community is that delta CP, neutrino masses, all these mixing angles, these are fundamental physics parameters. They're kind of like alpha, which we've measured really well, by the way. And we spend a lot of resources doing that. Maybe not at the same time, but we've been doing for more than 100 years. And this is sort of our legacy for the future. It is possible that we don't know what to do with these numbers, but I'm willing to believe that in the future, somebody will know how to handle these numbers, and we're helping them out by letting them know very, very precisely, again, if we find no more new physics, what these parameters are. And if that's the only thing we do, I think it's a good investment.
All right, so in the spirit of a true hybrid meeting, the Zoom session, she also was to say something there.
Sorry, I just wanted to give a quick quantitative answer to the question about the phase-in part of your question. So phase 1, we get the mass ordering absolutely for sure, unequivocally. In phase 1, if we are very lucky with the part of parameter space nature lives in, then we could get to start having some significance for CP violation. We need phase 2 for any sort of precision measurement of delta.
Thank you. That was very crisp. Okay, somebody is here tapping on the clock. And so do we have anything more from online? I think here we have a comment from Breeze. Yes, okay. And I think with that, we close the session. Or do we have time for one more? Okay, all right.
So I have a question. I think it is a short question for Mark. So it is about the plot delta CP sensitivity as a function of years of data taken. So in that plot, like, is there any assumptions involved about the cross-section models and the cross-section and flux systematics? Like, is it based on how much we know about this, or is it based on how much we will know by the time the detectors come online?
So the answer is yes. There is some assumption about the systematics in there, and probably Mark can give you the details.
Yeah, I think the biggest impact on the systematics is if you look at the, I'm assuming Yeah, okay. I'm assuming that you're referring specifically to the Dune example. So the main improvement in systematics is when in phase 2, the near detector upgrade comes online. And then one sees an improvement in the systematics related to the cross-section systematics. That's the biggest effect. I believe, and I'm going to look to Elizabeth, that otherwise the systematics stay roughly constant in the background as those plots evolve. Is that the various normalizations and other things. The key improvement, though, is the improvement in systematics due to the upgrade of the near detector.
So in short, Dune will do this data-driven with its own data from its own near detector. So basically, you take today's errors bars, and thanks to the near detector, they will shrink, will have a small impact on the final result. All right, with that, we really close now. It's 7:05, and the dinner is waiting, I understand. Thanks, everybody. Thanks to the speaker.